The universe around you isn't still. It's moving, growing, expanding in every direction, carrying galaxies farther apart in a silent, endless rhythm. In this vastness, our world is just a tiny spark, yet somehow we get to look up and wonder. So tonight, as you close your eyes, let's drift together through 100 facts about the expanding universe, a journey through time, light, and the infinite calm of cosmic space. Fact 1. The moment. The universe began, the birth of space and time. Have you ever wondered what the beginning really means? Not the beginning of a story or a life, but the beginning of everything. Imagine a moment when there was no space to move in, no time to pass, just a silent, infinite potential waiting to burst open. That's the moment the universe began. It's strange to think that time itself had a starting point. Before that instant there was no before. Space didn't exist, and neither did distance. Then, in less than a heartbeat, something happened. Not an explosion in space, but the creation of space itself. From a point smaller than an atom, energy expanded and cooled, and the first laws of physics took shape. This wasn't a loud or fiery moment like we often picture. It was quiet in a way that's hard to imagine, because sound needs space to travel through, and there simply wasn't any yet. The universe was smooth, simple, and unimaginably hot, filled with energy that would one day form everything we know: stars, planets, and people. Every second that passes, even now, is a continuation of that first instant. The clock that began then has never stopped ticking. When we look up at the night sky, we're seeing the story of that beginning still unfolding. It's humbling, really, knowing that everything started with a single flash of creation, and that we are still inside that same moment, billions of years later. Fact 2. The meaning of cosmic expansion. When astronomers talk about the expanding universe, they don't mean galaxies are flying apart like pieces from an explosion. It's more like space itself is growing, stretching the distances between everything inside it. Think of it like this. Picture dots drawn on a balloon. As you blow air into it, the dots move farther apart, even though they're not moving across the surface on their own. That's how the universe expands. Every bit of space is stretching equally, carrying galaxies with it like tiny specks on the cosmic balloon. This expansion is the reason the night sky is filled with galaxies that seem to drift away. The farther away one is, the faster it appears to move. That's not because of speed in the usual sense, it's because the space between us is growing. What's even more fascinating is that expansion doesn't happen inside galaxies or solar systems. Gravity holds those together tightly. Instead, expansion happens on the vast scales between galaxy clusters, the great cosmic ocean where gravity grows weak. The meaning of cosmic expansion, then, is simple but profound. The universe isn't just getting older, it's getting larger. Every moment new space is being made, quietly increasing the distance between distant galaxies. It's not a rush or a roar, just a slow, endless stretching of everything, everywhere. Fact 3. What scientists mean by the universe is stretching. When scientists say the universe is stretching, they don't mean galaxies are racing through empty space. They mean that space itself, the very fabric of reality, is expanding. Imagine the universe as a soft, flexible material. The galaxies aren't moving through it, they're being carried with it as it stretches. One of the easiest ways to picture this is to imagine baking a raisin loaf. As the dough rises, the raisins drift apart. They're not moving on their own. The dough between them is expanding. That's what scientists mean when they say the universe is stretching. Now, the tricky part is that this stretching doesn't affect everything equally. Here on Earth, and even within our galaxy, gravity keeps things tightly bound. We don't feel the universe stretching beneath our feet or between the stars of our Milky Way. But far beyond, between galaxy clusters, space expands, carrying light from distant galaxies with it, making their glow shift toward red. This redshift is like a cosmic fingerprint, a quiet reminder that the universe is still growing. Every beam of starlight reaching us has been stretched by this expansion, its colour softened by distance and time. So when scientists say space is stretching, what they're really describing is the calm, steady unfolding of the universe itself, a motion so vast and gentle that it reshapes reality, 1 inch of space at a time. Fact 4. The first instant after the Big Bang. Try to imagine the very first moment, the tiniest fraction of a second after everything began. It's almost impossible, because time itself had just started ticking. In that first instant, the universe was a storm of energy, incredibly dense and unimaginably hot. Space expanded faster than light, not because anything broke the rules, but because the rules were still being written. This phase is known as cosmic inflation. It lasted only a blink, but it changed everything that would ever exist. As the universe expanded, it cooled just enough for energy to turn into tiny particles, the building blocks of everything. Quarks and electrons, light and matter began to take form. The first few minutes saw the creation of hydrogen and helium, the simplest elements. It's strange to think that in those chaotic early seconds, the foundation for stars, galaxies, and eventually life was already being set. Everything that exists today can trace its history back to that instant. If you could somehow watch it happen, you wouldn't see a bright explosion. You'd see a uniform, glowing fog, smooth, silent, expanding in every direction. And though that moment ended long ago, its echo still surrounds us, frozen in faint microwave light that scientists can still detect today, a whisper from the first moment after everything began. Fact 5. The universe's expansion. Compared to a rising loaf of bread. Sometimes the simplest examples explain the biggest ideas. Picture a loaf of bread baking in the oven. As it rises, the dough expands and the raisins inside move farther apart. Not because they're moving through the dough, but because the dough itself is stretching. That's exactly how the universe expands. Galaxies are like raisins, not racing through space, but being gently carried apart as space itself grows. The oven isn't exploding, it's just rising, slowly, evenly, everywhere at once. What's fascinating is that every raisin would see all the others moving away, no matter which one you stood on. There's no center of expansion, just as there's no true center of the universe. Every point experiences space growing around it equally. And just like the bread dough doesn't expand inside the raisins, the universe's expansion doesn't stretch galaxies, stars, or planets. Their gravity keeps them together. It's only the vast emptiness between galaxy clusters that grows. This quiet comparison, a simple loaf of bread, captures something incredible. Our universe isn't a violent explosion in space, but a calm, ongoing rising of space itself. Every moment the dough stretches a little more, carrying everything gently apart. Somewhere inside that loaf, among billions of cosmic raisins, we're just one small speck, watching it all expand in silence. Fact 6. The cosmic microwave background, the oldest light. We can see, if you could turn your eyes into perfect cosmic detectors and look in every direction, you'd see something faint, ancient, and all around you. A soft glow that fills the entire universe. That glow is the cosmic microwave background, often called the oldest light we can see. It's not a light you can see with your eyes. It's more like invisible warmth. The afterglow left behind from when the universe was only about 380,000 years old. Back then, the young cosmos was hot, dense, and glowing. But as it expanded and cooled, that brilliant light stretched into gentle microwaves that still linger today. Astronomers first discovered it by accident in the 1960s. Two scientists, Arno Penzias and Robert Wilson, were trying to clear static from a radio antenna. No matter what they did, a faint hiss remained. They thought it was noise, maybe bird droppings on the dish, but it turned out to be the oldest signal in existence. They had stumbled upon the whisper of the early universe. Today, satellites like Planck and COBE have mapped that ancient glow in detail. The light isn't perfectly even. It has tiny ripples, like the faintest wrinkles on a calm pond. Those ripples were the seeds of everything we see today. Galaxies, stars, and planets. The cosmic microwave background is like a baby picture of the universe, frozen in time, showing us what it looked like when it first began to shine. Fact 7. How astronomers discovered the universe. Was expanding. A century ago, most people believed the universe was static, endless and unchanging. Stars seemed fixed, galaxies were barely known, and the idea of an expanding cosmos sounded absurd. But through telescopes, astronomers began to notice something strange. As they studied distant galaxies, they found that their light seemed stretched, shifted toward the red end of the spectrum. That shift meant the galaxies were moving away from us, and the farther away they were, the faster they seemed to go. It was as if the universe itself was growing. This discovery changed everything. Suddenly, the cosmos wasn't a still, eternal space. It was alive, expanding, and moving. The key observations came from work at Mount Wilson Observatory in California, where massive telescopes peered deeper into the heavens than ever before. What astronomers found was simple but profound. The universe had a history, a direction, and possibly even a beginning. From that point onward, the picture of the cosmos would never be the same. The discovery of expansion showed that we live inside a universe that's still unfolding, an endless, gentle stretching of time and space, happening quietly above our heads every second. Fact 8. Edwin Hubble's surprising discovery in the 1920s. In the 1920s, an astronomer named Edwin Hubble made one of the most important discoveries in science, though at first he might not have realized just how big it was. Back then, most scientists thought the Milky Way was the entire universe. Other patches of light in the sky, called nebulae, were believed to be part of our galaxy, but Hubble used a powerful telescope to study one of them, the Andromeda Nebula, and found something stunning. He measured the brightness of certain stars within it, and realized they were far too faint to be nearby. Andromeda wasn't a cloud within our galaxy. It was an entire galaxy of its own, millions of light-years away. That single realization expanded the known universe overnight. Suddenly, the Milky Way was just one of countless galaxies scattered through the cosmos. But Hubble didn't stop there. By measuring the light from dozens of galaxies, he noticed a clear pattern. Nearly all of them were moving away from us, and the farther they were, the faster they went. This became known as Hubble's law. It showed that the universe wasn't static. It was expanding. The discovery transformed astronomy and confirmed that space itself was stretching. From that moment on, humanity's view of the cosmos grew larger than ever imagined. Fact 9. The redshift, a clue, hidden in starlight. Every star and galaxy sends out light, and inside that light are tiny fingerprints that tell us incredible things. Scientists call this pattern the spectrum. When astronomers look at the light from faraway galaxies, they see those fingerprints shifted slightly toward the red end. That small change is known as redshift, and it's one of the greatest clues about the universe's expansion. Here's how it works. When something moves away from you, the waves it sends out stretch. You can hear it with sound, like an ambulance siren dropping in pitch as it drives away. The same happens with light. When galaxies drift away, their light waves stretch, turning redder. This redshift is how we know the universe is growing. The farther a galaxy is, the more its light is stretched, meaning it's moving away faster. It's not because the galaxies are speeding through space, it's because space itself is stretching. That faint shift, hidden in the glow of distant stars, tells the entire story of the cosmos. It's the quiet proof that space is expanding, and has been since the very beginning. What looks like a small detail in a telescope spectrum is actually the signature of an entire universe in motion. Fact 10. Why galaxies move away from each other. If you look at the universe on a grand scale, you'll notice something curious. Most galaxies seem to be moving apart. But it's not because they're all flying away through space like sparks from a fire. It's because space itself is expanding, carrying them along. Imagine you're sitting on a raft in the middle of a calm lake, and suddenly the lake starts stretching in all directions. You wouldn't see the water rushing past you. You just notice that every other raft is drifting farther away. That's exactly what's happening to galaxies. The farther a galaxy is, the more space there is between us, and the faster that space expands. That's why distant galaxies seem to move away quicker than nearby ones. This doesn't mean we're at the center of the universe. It looks that way from any galaxy's point of view. Everywhere in the cosmos, the same thing is happening. It's important to remember that galaxies themselves aren't growing apart internally. The stars, planets, and systems inside them are bound tightly by gravity. Expansion only happens in the vast distances between galaxy clusters, the quiet stretches of space where gravity is weak. So when astronomers say galaxies are moving away from each other, it's not about motion in the usual sense. It's about the steady, gentle stretching of the universe itself, a cosmic rhythm that's been going on for billions of years and will likely continue for billions more. Fact 11. The invisible fabric of space-time. Expanding everywhere at once. Think of space not as emptiness, but as a kind of invisible fabric, a soft, flexible stage that everything in the universe sits upon. That fabric is what scientists call space-time. It bends when something heavy like a planet or a star rests on it, and it stretches as the universe expands. What's remarkable is that this expansion doesn't happen from a single point. It's happening everywhere, all at once. Every region of space is quietly stretching, increasing the distance between galaxies even while we stand still. It's not that galaxies are moving through space. It's that space itself is growing beneath them. If you could somehow freeze the universe for a moment and then restart it, you'd see this stretching begin again everywhere at once. Between distant galaxies, between clusters, even between points of light billions of light years apart. You don't notice it on small scales because gravity and other forces hold things together. But on the vast cosmic stage, that expansion is unstoppable. It's the reason why the light from faraway galaxies is redshifted, and why the night sky shows us a universe still unfolding. The invisible fabric of space-time is constantly expanding beneath everything, a silent movement that began at the birth of time itself and continues, quietly, everywhere around us. Fact 12. Why expansion happens between galaxies, not within them. The universe is growing, but strangely, you don't feel it. Your room doesn't stretch. The solar system stays the same size. Even our galaxy holds its shape. That's because the expansion of the universe only happens between galaxies, not within them. Here's why. Expansion is a large-scale effect. It stretches space over huge distances where gravity is weak. Inside galaxies, gravity's pull is much stronger. It binds stars, planets, and entire systems tightly together, resisting the gentle tug of cosmic expansion. You can think of it like this. If the universe were a vast ocean, galaxies would be little whirlpools, regions where gravity keeps matter swirling in place, even as the larger ocean slowly expands around them. Between those whirlpools, however, the water, or in this case, space, stretches. Galaxies drift apart not because they're moving through space, but because the space between them is growing. So while the distances between galaxy clusters increase, the galaxies themselves remain intact, their stars held fast by gravity. It's a balance that lets the universe expand without tearing itself apart, a cosmic dance of motion and stability that's been going on for billions of years. Fact 13. How cosmic inflation changed everything in a fraction of a second. Right after the universe began, something incredible happened. In less than a blink, far faster than we can truly imagine, the universe expanded faster than light. This event is known as cosmic inflation, and it changed everything. Before inflation, the universe was unimaginably small and dense, filled with pure energy. Then, in a fraction of a second, it stretched billions of times in size. This expansion didn't push matter outward like an explosion. It expanded space itself, smoothing it out, evening its temperature, and setting the stage for galaxies and stars to form. Without inflation, the universe might have been uneven, chaotic, or clumped in strange ways. Instead, it became astonishingly uniform with only tiny ripples, the same ripples we see today in the cosmic microwave background. Those tiny differences became the seeds of everything that exists. Cosmic inflation is one of the most mysterious moments in the universe's story. It was brief, silent, and invisible, yet it defined everything that would follow. It's strange to think that all of space, all of time, and every particle around us came from that tiny flash of expansion that lasted less than a heartbeat but shaped eternity. Fact 14. What the universe looked like. Seconds after it began. If you could somehow look back to the first few seconds after the universe began, you wouldn't see stars or galaxies. You'd see a glowing fog of energy and particles, chaotic, bright, and hot beyond imagination. The young universe was dense and filled with light, but no atoms or structures yet existed. Everything was a mix of fundamental particles, protons, neutrons, and electrons, bouncing around in a sea of radiation. As the seconds passed, the universe began to cool, and particles started to combine. Protons and neutrons formed the first atomic nuclei, mostly hydrogen and helium. It was still too hot for atoms to fully form, but the building blocks were ready. During this time, the universe was expanding rapidly, and light couldn't travel far because it kept scattering off free electrons. It was like being inside a glowing cloud where everything was bright, but nothing was clear. Only much later, when the universe cooled enough for atoms to form, did light finally escape, creating the cosmic microwave background we see today. But in those early seconds, the universe was alive with energy, shaping everything that would come after, a newborn cosmos still finding its balance. Fact 15. The earliest atoms forming in a young cosmos. Hundreds of thousands of years after the beginning, the universe had finally cooled enough for something extraordinary to happen. Atoms could form. Before this moment, space was filled with a glowing fog of charged particles. Light couldn't travel far because it was constantly bouncing off electrons. But as temperatures dropped, protons and electrons began to combine, forming the first atoms, mostly hydrogen, with a bit of helium. This process is known as recombination. When it happened, the universe transformed. The fog cleared, and light was free to move through space for the first time. That same light still travels today as the cosmic microwave background, the faint afterglow of the universe's youth. These first atoms were the foundation for everything else. Over time, they gathered under gravity's pull, forming clouds, then stars, and eventually galaxies. From these early atoms came every element, every world, and every living thing. It's peaceful to imagine that quiet turning point, when a hot, chaotic universe cooled just enough for matter to take shape. The moment when light could finally shine freely, and the cosmos began to look a little like the one we see today. Fact 16. The first light. Breaking through the cosmic fog. For hundreds of thousands of years after the universe began, everything was hidden behind a glowing fog. The cosmos was filled with charged particles that scattered light in all directions, making the universe bright but unclear, like looking through thick mist. Then something beautiful happened. As the universe expanded, it cooled enough for those particles to combine into atoms. Suddenly light no longer bounced around. It could travel freely for the first time. This moment, called recombination, marked the birth of the universe's first light. That ancient glow still exists today as the cosmic microwave background, the faint radiation that surrounds us everywhere. It's the universe's first clear signal, a soft whisper from when space first became transparent. Imagine standing at the edge of that moment, watching as the fog slowly fades. The light that once couldn't escape now spreads across the vastness of space, continuing its journey for billions of years. It's not the light of stars or galaxies, those hadn't formed yet, but the very first light to ever shine across the universe. It's humbling to know that this ancient glow is still reaching us. When astronomers detect it with their instruments, they're not just seeing old light, they're seeing the universe's first sunrise. Fact 17. How galaxies began to take shape. Once the first atoms formed and the universe became clear, a new story began, the story of galaxies. At first, everything was almost perfectly smooth, but tiny differences in density, little clumps of matter left over from the early universe, gave gravity something to work with. Over millions of years, those clumps began to pull in more material. Slowly they grew denser, forming massive clouds of gas. As these clouds collapsed under their own weight, stars began to ignite inside them. Groups of stars gathered together, creating the first galaxies. They were small and irregular at first, glowing faintly in the early darkness. Over billions of years, those galaxies collided, merged, and grew into the vast spirals and ellipticals we see today. Our own Milky Way was built from countless smaller galaxies joining together, a slow, graceful process that took billions of years. The galaxies we see now are the result of that long cosmic evolution, each one a collection of billions of stars bound by gravity, shining across expanding space. From quiet beginnings, the universe became alive with light, a sea of galaxies forming from the faint ripples of the first atoms. Fact 18. The oldest known galaxy we've ever seen. When astronomers look far into the universe, they're also looking back in time. Light takes years, even billions of years, to reach us. So the deeper we look, the younger the universe appears. Using powerful telescopes like the James Webb Space Telescope, scientists have spotted galaxies that formed just a few 100 million years after the beginning. One of the oldest known so far is galaxies E13, a small, faint galaxy whose light has travelled for over 13 billion years to reach us. It's incredible to think about. That tiny smudge of light we see today began its journey before our Milky Way even existed. That galaxy is ancient, yet we're only seeing it now because space has stretched its light for billions of years. What's fascinating is that these early galaxies look nothing like the ones we see nearby. They're smaller, rougher, and bursting with new stars. They're the cosmic pioneers, the first structures to shine in a dark universe. Every time we find an older galaxy, we're seeing deeper into our own history, a glimpse of what the cosmos looked like when it was still learning to build light and structure. Fact 19. The speed of the universe's expansions today. You might wonder, just how fast is the universe expanding right now? The short answer, very fast and still speeding up. Astronomers use something called the Hubble constant to measure the rate of expansion. On average, for every million parsecs, about 3.26 million light-years, of distance, space itself expands by roughly 70 kilometers per second. That means a galaxy 10 billion light-years away is receding from us at incredible speeds, faster than light, though not in the usual sense. It's not that galaxies are breaking any rules, it's that space itself is stretching, carrying them farther apart. The farther away something is, the faster it appears to move. Even more surprising, this expansion is accelerating. A mysterious force called dark energy seems to be driving it, pushing galaxies apart more strongly over time. We don't fully understand why, but we can observe its effects across the sky. So while our daily lives feel still and solid, the truth is the universe is constantly in motion, quietly expanding faster and faster every single moment. Fact 20. How astronomers measure that speed. Measuring the expansion of the universe sounds impossible, but astronomers have found clever ways to do it. They rely on light, the most honest storyteller in the cosmos. One key tool is the redshift. When a galaxy's light is stretched as it travels through expanding space, it shifts toward red. By measuring how much the colour of that light has shifted, scientists can tell how fast the galaxy is moving away. Another method uses standard candles, special types of stars or supernovae that always shine with a known brightness. By comparing how bright they appear from Earth, astronomers can figure out their distance. When they combine that distance with redshift data, they can calculate how quickly the universe is expanding. Modern telescopes, like the Hubble Space Telescope and the James Webb, refine these measurements by observing galaxies billions of light-years away. With every observation, we understand the rhythm of cosmic expansion a little better. It's fascinating that by studying faint ancient light, we can measure the motion of the entire universe, a gentle, ongoing stretch that began billions of years ago and still continues, everywhere, even as we speak. Fact 21. The Hubble constant. The number that defines expansion. At the heart of our understanding of an expanding universe lies a single number, the Hubble constant. It's the value that tells us how fast the universe is growing at this very moment. First measured by astronomer Edwin Hubble in the 1920s, it showed that galaxies farther from us move away faster, proof that the universe itself is stretching. Today, this constant is measured in kilometers per second per megaparsec, meaning that for every million parsecs, about 3 million light-years, of distance, galaxies recede at a certain speed. But here's where it gets fascinating. Different methods give slightly different results. Measurements from nearby galaxies using stars and supernovae suggest one value, while measurements from the early universe, using the cosmic microwave background, suggest another. Even a tiny difference matters, because it could mean we're missing a piece of cosmic physics. Maybe dark energy behaves differently over time, or maybe there's something new in how space itself evolves. The Hubble constant isn't just a number, it's a clue to the universe's true story. Each new measurement brings us closer to understanding not only how the universe expands, but why. Fact 22. Why scientists still debate the universe's true rate of growth. You might think that after a century of studying the cosmos, scientists would have pinned down the universe's rate of expansion. But the truth is, it's one of the biggest mysteries in modern astronomy. Two main techniques disagree. One measures the expansion by observing distant galaxies and supernovae, the local universe. The other studies patterns in the cosmic microwave background, the early universe. The problem? Their answers don't match. This difference, known as the Hubble tension, is more than just a minor measurement error. It could mean our current theories about the universe need adjusting. Maybe the laws of physics have changed slightly over billions of years, or perhaps something unknown, like a new form of energy or matter, is influencing the cosmos. For now, scientists continue refining their tools and rechecking their data, trying to bridge the gap between the two results. What's exciting is that this debate might lead to a major discovery, one that reshapes how we understand time, space, and everything between. Fact 23. The mysterious force. Known as dark energy, in the late 1990s, astronomers made a shocking discovery. The expansion of the universe isn't slowing down, it's speeding up. Something unseen was pushing galaxies apart faster and faster. They called it dark energy. Dark energy isn't something we can see or touch, but its influence is everywhere. It makes up about 70% of the entire universe, yet we barely know what it is. It doesn't glow, it doesn't cluster, and it seems to work in perfect balance, stretching space itself. Some scientists think it's a property of space, an energy that increases as space grows. Others suggest it's a new kind of field or even a sign that our understanding of gravity is incomplete. Whatever its nature, dark energy is shaping the fate of the cosmos. It's the quiet driver behind every galaxy drifting farther away, the invisible current beneath the surface of reality itself. For now, it remains the most mysterious force we know, vast, subtle, and everywhere at once. Fact 24. How dark energy accelerates the expansion of space. Imagine space as a stretchy fabric with tiny amounts of built-in energy. As the universe expands, more of that fabric appears, and with it, more energy. This creates a kind of cosmic feedback loop. The more space there is, the more dark energy exists to drive expansion even faster. That's why galaxies are not just moving away from one another, they're speeding up over time. Dark energy acts against gravity, the force trying to pull everything together. The larger the universe becomes, the more dark energy dominates. To understand it, think of blowing up a balloon. At first, you have to push hard, but as it expands, the process seems to quicken. Similarly, once the universe reached a certain size, dark energy began to take over, stretching space faster and faster. This acceleration doesn't tear galaxies apart. It acts only on the vast distances between them. Inside galaxies, gravity still rules. But across the immense voids of space, dark energy leads the dance, guiding the universe's slow but steady quickening. Fact 25. Why the universe is expanding faster than before. When astronomers first realized the universe was speeding up, it challenged everything they thought they knew. Until then, the common belief was that expansion would gradually slow due to gravity, but instead, observations of distant supernovae revealed something startling. The universe was expanding faster now than it used to. This acceleration is driven by dark energy. As the universe grows, the amount of dark energy doesn't thin out, it stays constant or even increases. That means its effect becomes stronger over time, Billions of years ago, matter and gravity played a bigger role, pulling galaxies together. But as space expanded, dark energy began to dominate, overpowering gravity's hold. The result is the cosmic acceleration we see today. It's a quiet but relentless process. Every billion years, galaxies drift farther apart, their light stretching more and more as space expands beneath it. And unless dark energy changes or fades, the universe will keep accelerating, an endless, gentle stretching into the deep future. Fact 26. The idea that empty space itself has energy. It sounds strange, doesn't it? The thought that nothing could actually be something. But that's exactly what scientists discovered about empty space. It's not really empty at all. Even in the darkest, quietest corners of the universe, space hums with invisible energy. Tiny, fleeting particles pop in and out of existence, like sparks on a cosmic sea. This energy, sometimes called vacuum energy, may be what fuels the expansion of the universe itself. Albert Einstein once suggested that space might contain an energy of its own, a built-in force that resists collapse. Decades later, that idea came back as a possible explanation for dark energy, the mysterious push behind the universe's accelerating growth. So when we look at the sky and see stars scattered across vast emptiness, that emptiness isn't truly void. It's alive with subtle motion, unseen power, and endless possibility, the quiet heartbeat of the cosmos itself. Fact 27. How galaxies drift apart over billions of years. Imagine painting tiny dots on a balloon. As you blow it up, the dots move away from one another, not because they're flying through the air, but because the surface itself is stretching. That's exactly how galaxies drift apart. It's not that galaxies are racing through space at incredible speeds, it's that space itself is expanding. Over billions of years, this expansion slowly increases the distance between galaxy clusters. Within each galaxy, gravity holds everything together tightly, but between galaxies there's nothing to resist the stretch. What's amazing is how gentle this process is. You wouldn't notice it if you could somehow watch in real time. But across billions of years, the movement becomes enormous, a silent ballet of light drifting ever farther apart. Every photon of starlight we see from distant galaxies has travelled across this expanding fabric, stretched thinner and redder by the journey. A quiet reminder that the universe is always in motion. Fact 28. The growing distance between the Milky Way and Andromeda. The Milky Way and Andromeda are two giant spiral galaxies floating in the same cosmic neighbourhood, about 2.5 million light-years apart. That's close, astronomically speaking. But here's the twist. While most galaxies move away due to the universe's expansion, these two are actually drifting toward each other. Gravity between them is stronger than the cosmic expansion that usually pushes galaxies apart. So instead of separating, they're slowly inching closer, at about 110 kilometers per second. Over billions of years, that distance will close completely. This gentle pull shows that cosmic motion isn't just about expansion. Local gravity can still win when galaxies are close enough. The space between them may be stretching, but their mutual attraction is stronger. Someday, their stars, planets, and dust will merge into one enormous galaxy. A breathtaking example of how even in an expanding universe, some things are still drawn together. Fact 29. The eventual collision between those two galaxies. Roughly 4 billion years from now, the night sky over Earth, or whatever remains of our solar system, will look dramatically different. A bright, glowing shape will dominate the heavens, the approaching Andromeda galaxy. When it finally collides with the Milky Way, it won't be an explosion or violent crash as we imagine. The space between stars is so vast that very few will actually collide. Instead, the two galaxies will swirl together gracefully, their stars pulled into long tidal streams that twist and blend over time. Eventually they'll settle into a single massive elliptical galaxy, sometimes called Milkomeda. The night sky would glow with billions of new stars, forming and dying as the cosmic dust stirs anew, though our sun will be near the end of its life by then. This event marks one of the grandest slow dances in the cosmos, a reminder that creation and transformation go hand in hand, even on a galactic scale. Fact 30. What galaxy mergers, tell us about cosmic motion. Galaxy mergers might sound rare, but they're actually a normal part of the universe's life cycle. Nearly every large galaxy, including our own, has grown through a series of mergers, swallowing smaller galaxies and blending with others over billions of years. These collisions reveal how matter gathers and moves through the universe. They show us that cosmic motion isn't random chaos. It's shaped by gravity's quiet, steady pull. Every merger reshapes the galaxies involved, sparking waves of new star formation as clouds of gas and dust collide. In a way, galaxy mergers are like chapters in the universe's story, moments of both destruction and creation. They explain how galaxies evolve, how stars are born in brilliant bursts, and how the cosmos continues to grow in complexity and beauty. Even as space stretches wider, gravity still weaves galaxies together, ensuring that the universe remains connected, not by proximity, but by the shared rhythm of motion and change. Fact 31. How expansion shapes the cosmic web of galaxies. When we look deep into space, the universe doesn't appear random. Instead, it forms a vast web, a delicate network of galaxies, clusters, and filaments stretching across unimaginable distances. This grand structure is known as the cosmic web, and expansion plays a huge role in shaping it. After the Big Bang, tiny fluctuations in density appeared, small ripples in an otherwise smooth sea of energy. Over billions of years, gravity amplified those ripples. Regions with a little more matter pulled in even more, forming galaxies and clusters, while emptier areas grew into vast cosmic voids. As the universe expanded, these patterns stretched, like ink spreading through water. Expansion didn't erase the structure, it magnified it, allowing clusters to separate into threads and sheets that now span hundreds of millions of light years. So, the next time you see a map of galaxies, think of it as a frozen snapshot of motion, the universe expanding, stretching, and weaving itself into one enormous cosmic web. Fact 32. The vast filaments that connect clusters across the universe. If you could zoom out far enough, you'd see something breathtaking. Galaxies connected by enormous filaments of matter, like glowing bridges across the darkness. These filaments are the backbone of the universe, made up of dark matter, gas, and billions of galaxies linked together in strands that can reach hundreds of millions of light years long. They form where gravity has pulled matter into thin, stretched-out shapes, the remains of ancient ripples from the early universe. Between them lie the cosmic voids, enormous empty spaces where very few galaxies exist. Astronomers use computer simulations and powerful telescopes to trace these filaments, revealing a universe that looks almost like a living organism, with clusters as bright nodes and filaments as the arteries connecting them. These structures remind us that even across cosmic distances, everything is part of something larger. The galaxies we see at night are not isolated. They're threads in a grand interconnected web that stretches across the entire universe. Fact 33. Why cosmic voids are just as important as galaxies. It's easy to focus on the galaxies, the brilliant lights, the clusters, the endless spirals, but the empty regions, the cosmic voids, tell an equally important story. Voids make up most of the universe's volume. These are vast, quiet expanses where galaxies are few and far between. At first they might seem like gaps, but they help shape how the universe expands. As matter gathers into filaments and clusters, the voids grow larger, gently pushing galaxies outward. Studying these voids helps astronomers understand dark energy and the overall geometry of the cosmos. They act like cosmic laboratories, showing how gravity and expansion interact in places almost free from matter's pull. So while galaxies sparkle and steal our attention, it's the darkness between them that defines the grand pattern. The universe isn't just built of light, it's built of balance, shaped equally by what's there and what's not. Fact 34. The scale of the observable universe. Try to imagine this. The farthest galaxies we can see are over 46 billion light-years away. That's the radius of the observable universe, the portion of the cosmos from which light has had time to reach us since the beginning. But here's the mind-bending part. The universe itself is much larger than that, possibly infinite. The limit isn't physical, it's temporal. Light simply hasn't had enough time to travel from farther regions. Within our observable bubble lies everything we can measure: galaxies, clusters, radiation, and the faint traces of the Big Bang. Yet beyond that edge, space continues to expand faster than light can travel. It's humbling to realize that every telescope, every discovery, every image of a distant galaxy represents just a small fraction of all that exists. What we see is a window, a cosmic horizon, into a universe far bigger than our minds can grasp. Fact 35. How far light can travel in cosmic time. Light is fast, about 300,000 kilometers per second. But even at that speed, crossing the universe takes ages. The light we see from the sun is 8 minutes old. From the nearest star, it's 4 years old. From distant galaxies, it's billions of years old. Because of this, when we look far away, we're also looking back in time. Each photon carries a story from a different era of the universe's history. The farther the light has travelled, the younger the universe was when it began its journey. There's a limit to how far we can see, the cosmic light horizon. Beyond it, the universe has expanded so much that light from those regions will never reach us. So when you gaze at the night sky, you're not just seeing space, you're seeing time itself stretched across the darkness. Every twinkle is a message from the past, travelling for billions of years just to reach your eyes. Fact 36. What lies beyond the visible edge of space. When we talk about the edge of the universe, it's not really a wall or a border. It's a limit to what we can see. Beyond that limit, the universe continues, vast and unending, but hidden from our view. The light from those distant regions hasn't had enough time to reach us yet. Imagine standing in a foggy field with a lantern. You can only see as far as the light travels through the mist. Beyond that, there's still more field, but it's lost in the haze. That's how the universe looks to us. What lies beyond could be more galaxies, stars and clusters, stretching endlessly in every direction. Or perhaps regions of space so different that they follow other physical rules. Maybe even other bubbles of universe formed in the same cosmic beginning. No one knows for sure. But what's certain is this: our universe doesn't end where our sight does. The visible edge is just the beginning of a much larger unseen reality, one that will always remain partly beyond reach. Fact 37. The difference between the observable and total universe. The observable universe is everything we can detect with light, radio waves, and other signals. It stretches about 46 billion light-years in every direction from Earth, a vast sphere of cosmic history. But the total universe is almost certainly far larger. It could be thousands, millions, or even infinite times bigger than what we can see. The reason we can't observe it all is simple. The universe has a finite age, and light travels at a finite speed. Since the Big Bang, only a limited amount of time has passed, meaning only a limited amount of light has reached us. Beyond that, space continues to exist and expand, but it's forever out of view. In a sense, the observable universe is like a small bubble inside an ocean of cosmic space. We can measure what's inside our bubble, but the rest remains mysterious, waiting silently beyond the horizon of time. Fact 38. How cosmic expansion hides parts of the universe. Forever. Here's a strange but true idea. There are galaxies we'll never see, not because they're too faint, but because the universe is expanding faster than light can bridge the gap. As space stretches, distant galaxies move away from us, not through space, but with space itself. The farther away they are, the faster they recede. Eventually, some drift beyond a point where their light can ever reach us. That means even if those galaxies are still out there, their last signals are frozen at the edge of visibility, fading into darkness. From their point of view, the same happens to us. We too slip away from their universe of light. In time, cosmic expansion will hide most of the universe from view. Distant galaxies will vanish one by one, leaving only our local cluster visible. The universe will seem quieter, not because it's smaller, but because expansion has drawn the curtains on the rest. Fact 39. The concept of the cosmic horizon. The cosmic horizon is like the ultimate limit of sight. the farthest distance from which light has had time to reach us since the universe began. Beyond it lies everything we'll never be able to see or measure. It's not a physical boundary, but a time boundary. As the universe ages, the horizon slowly expands, revealing new regions of space. But because the universe itself is also expanding, some distant places stay forever beyond reach. Think of standing on a shore, watching the ocean. No matter how far you look, you can't see beyond the curve of Earth, yet you know there's more ocean out there. The cosmic horizon is like that, a reminder that what we see is only a small fraction of the whole. It's one of the universe's quiet paradoxes. Even as our tools grow sharper, there will always be a point beyond which observation ends, and imagination begins. Fact 40. Why some galaxies move faster than light, and why that's okay. It sounds impossible, doesn't it? Some galaxies are moving away from us faster than the speed of light, but it doesn't break any cosmic rules, because it's not the galaxies themselves speeding through space, it's space that's expanding between us. Einstein's theory of relativity says nothing can move through space faster than light, but it doesn't limit how fast space itself can expand. As the universe stretches, the fabric of space carries galaxies with it, increasing their distance at faster and faster rates the farther away they are. So when astronomers say a galaxy's recession speed exceeds light speed, it's a sign of expansion, not motion. Those galaxies aren't racing through the universe, they're being carried along by it. It's one of the most mind-bending truths of cosmology. The universe can grow faster than light can travel, and that's perfectly fine. Because in the end, light and space are two parts of the same grand story. One expanding, one chasing, both shaping the view we call the cosmos. Fact 41. The illusion of speed in an expanding space. When astronomers say galaxies are racing away from us, it might sound like they're moving through space at incredible speeds. But that's not quite true. It's space itself that's stretching. The galaxies aren't flying apart, they're being carried along as the universe expands. It's a bit like dots on the surface of an inflating balloon. The dots don't move on their own, but as the balloon expands, the distance between them grows. From any one dot's point of view, every other dot seems to be moving away, even though none of them are travelling across the surface. This creates the illusion of motion, a trick of perspective caused by expansion. The farther away something is, the faster it appears to be moving, not because it's speeding through the cosmos, but because there's more space between us to stretch. It's one of the universe's gentlest deceptions, showing a speed where there is only growth, motion where there is only change in the shape of space itself. Fact 42. How expansion stretches the wavelengths of ancient light. Light travels in waves, and just like waves on the ocean, those wavelengths can stretch. As the universe expands, it stretches the very fabric of space, and with it, every beam of light moving through it. This process is called redshift. Light that once shone bright and blue from young galaxies billions of years ago is now stretched into longer, redder wavelengths by the time it reaches us. The farther away the source, the more the light is stretched, a record of the universe's expansion written in colour. Even the faint glow left over from the Big Bang, the cosmic microwave background, has been stretched over billions of years, turning from a blinding white-hot light into the soft, cold microwave radiation we detect today. So, when we look at distant galaxies or ancient starlight, we're not just seeing light, we're seeing the stretch marks of time, gentle traces of the universe's long, slow expansion. Fact 43. The cooling of the universe. As it expands, at the very beginning, the universe was unimaginably hot, a dense ocean of energy where particles and light constantly collided. But as space expanded, everything began to cool. This cooling wasn't caused by a loss of energy, but by stretching. As the universe expanded, light waves lengthened and particles spread apart, lowering the overall temperature. Over billions of years, that blazing heat softened from billions of degrees to just a few degrees above absolute zero. It's a natural side effect of growth. Just as air cools when it expands, the universe's expansion spreads its energy thinner and thinner across space. Today, the universe still glows faintly with that leftover warmth. Not enough to feel, but enough for our instruments to detect. A quiet reminder that everything once burned together, before expansion turned fire into cold and chaos into calm. Fact 44. The fading heat of the Big Bang over time. If you could travel back to the first moments after the Big Bang, you'd find yourself surrounded by a sea of brilliant light and heat, a universe glowing with intense radiation. But as the cosmos expanded, that fire began to fade. The light that once filled space with brightness stretched and cooled, shifting from visible light to infrared, then to microwaves. Today, that same energy is still here, but it's incredibly faint. A whisper of heat left over from creation, spread thin across the sky. This cooling process continues even now. Every second as the universe expands, that background glow loses a little more warmth. Billions of years from now, it will fade even further, growing colder until it becomes nearly undetectable. The fading heat of the Big Bang is the universe's memory, the soft echo of its fiery birth, still drifting through space, still telling its story in silence. Fact 45. How cosmic background radiation maps the early universe. The cosmic microwave background, often called the afterglow of creation, is the oldest light we can see. It was released when the universe was only about 380,000 years old, a time when it finally became cool enough for atoms to form and light to travel freely. To the naked eye, this glow is invisible, but with special telescopes, scientists can detect it as a faint microwave signal spread evenly across the sky. Tiny variations in that signal, just millionths of a degree, reveal the universe's earlier structures. Those faint patterns are like a baby picture of the cosmos, showing where matter was slightly denser or thinner. Over billions of years, those tiny differences grew into galaxies, stars, and planets. By studying this ancient light, astronomers have mapped the shape, age, and composition of the universe itself. It's one of the greatest discoveries in science, proof that even after billions of years, the first light still shines, quietly painting a portrait of our cosmic beginning. Fact 46. What tiny ripples in that radiation tell us about creation? When scientists look closely at the cosmic microwave background, that faint glow left from the early universe, they notice something fascinating. It's not perfectly smooth. There are tiny ripples, slight differences in temperature scattered across the sky. Those ripples are more than random noise. They're fingerprints of creation itself, the earliest signs of structure in the universe. Each tiny variation marks a place where matter was a little denser or thinner than average. Over billions of years, those small differences grew under gravity's pull, forming galaxies, stars, and eventually everything we see today. By mapping these ripples, scientists can measure the universe's age, its composition, and even how fast it has expanded. They reveal how energy turned into matter, how light began to move freely, and how order slowly rose from chaos. In a way, those ancient ripples are the universe's first recorded memory, a cosmic photograph of the moment structure began, written across the sky for all of time. Fact 47. The link between expansion and cosmic time. In our daily lives, time feels steady. A second is a second, whether you're on Earth or looking up at the stars. But on a cosmic scale, time and expansion are deeply connected. One shapes the other. As the universe expands, the flow of time changes with it. In the early, dense universe, time moved differently. Everything happened at incredible speed. As expansion continued, the universe slowed and cooled, and so did the rhythm of cosmic time. This means that time isn't just something that passes, it's part of the structure of the universe itself. Every stage of cosmic history has its own tempo, from the rapid unfolding of the Big Bang to the slow drift of galaxies today. So when we measure expansion, we're also measuring time's journey, the heartbeat of the cosmos ticking slower as space stretches wider. Fact 48. Why? Time and space cannot be separated. We often think of space as one thing and time as another, as if they were separate ingredients. But Einstein showed that they're woven together into a single fabric called space-time. You can't move through space without also moving through time. The two are connected, bending and stretching together depending on gravity and motion. A massive object, like a star or planet, doesn't just sit in space. It curves space-time around it, shaping how everything nearby moves and how time itself flows. This unity explains why expansion affects both space and time. As the universe expands, not only do galaxies drift apart, but the pace of time changes slightly too. Space-time itself is what's growing, not just the emptiness between stars. In a very real sense, we all live inside the fabric of space-time, carried along as it stretches and evolves, the stage and the story unfolding as one. Fact 49. The role of general relativity in understanding expansion. Before Einstein, people imagined the universe as static, unchanging and eternal. But his theory of general relativity changed everything. It described gravity not as a force pulling objects together, but as the warping of space-time caused by mass and energy. When Einstein's equations were applied to the universe as a whole, they revealed something surprising. The cosmos couldn't stay still. Space had to be expanding or contracting. The mathematics refused to allow a frozen, motionless universe. Later, observations by Edwin Hubble confirmed what the equations had hinted. Galaxies were moving apart, and the universe was indeed expanding. General relativity became the key to understanding not only gravity, but also the universe's evolution. It showed that space itself can stretch, time can curve, and the cosmos can change. A living, dynamic creation rather than a fixed one. Fact 50. How Einstein's equations predicted a dynamic universe. When Einstein first developed his equations of general relativity, they described a universe in motion, one that either expanded or contracted. But that idea felt so strange to him that he added a small correction, a term called the cosmological constant, to make the equations allow a static cosmos. Years later, when Edwin Hubble discovered that galaxies were receding from us, Einstein realized his original equations had been right all along. The universe was expanding, dynamic, not still. He famously called his added constant his greatest mistake. Ironically, that same constant later returned as a possible explanation for dark energy, the force driving today's accelerated expansion. Einstein's math had predicted it from the beginning. The universe isn't a fixed backdrop. It's alive with motion, time, and change, a vast flexible fabric that continues to unfold just as his equations foretold. Fact 51. Why Einstein once doubted his own theory. When Albert Einstein finished his theory of general relativity in the early 1900s, it completely redefined how scientists understood space and time. His equations showed that the universe couldn't remain still. It had to expand or contract. But this idea didn't match what people believed at the time. Most scientists thought the universe was eternal and unchanging. Troubled by that conflict, Einstein began to doubt his own equations. Instead of trusting what the math said, he tried to adjust it to fit what the world expected. He added something new, a small correction to stop the universe from moving. In doing so, he silenced his own theory's boldest prediction. It would take years, and new discoveries by astronomers, to show that his original work had been right all along. The universe was indeed expanding. Sometimes even the greatest minds hesitate when their discoveries seem too strange to believe. Fact 52. The story of the cosmological constant. The cosmological constant began as a patch, a mathematical idea Einstein invented to keep the universe from collapsing or expanding. It acted like a hidden pressure inside space, pushing outward to balance gravity's inward pull. At first, it seemed like a clever fix. But when Edwin Hubble later found that galaxies were moving away from each other, proving the universe was expanding, Einstein realized he didn't need that constant at all. He reportedly called it his greatest blunder. Yet the story didn't end there. Decades later, scientists discovered that the universe's expansion is actually speeding up, and they brought the cosmological constant back to life. Today, it may be the key to understanding the mysterious force known as dark energy. What began as Einstein's correction has turned into one of the most profound clues in modern cosmology. Fact 53. How modern physics revived Einstein's mistake. For much of the 20th century, Einstein's cosmological constant was forgotten. But in the late 1990s, astronomers studying distant exploding stars made a shocking discovery. The universe's expansion wasn't slowing down. it was accelerating. Something unseen was driving galaxies apart faster and faster. Scientists needed a name for this strange invisible energy-filling space, and they found it in Einstein's old equation. The cosmological constant returned, no longer a mistake but a vital piece of the puzzle. Now physicists use it to describe dark energy, the mysterious pressure that stretches the fabric of space. What Einstein once removed, modern science restored, showing that even discarded ideas can hold the answers to the universe's greatest mysteries. Fact 54. The universe, as a balancing act between gravity and expansion. The universe is like a grand tug-of-war. On one side, gravity pulls everything inward, drawing galaxies and matter together. On the other, expansion pushes outward, stretching space itself. For billions of years, these two forces have shaped everything: the speed at which galaxies drift apart, the formation of stars and clusters, even the fate of the cosmos. If gravity were stronger, the universe might have collapsed back on itself long ago. If expansion had dominated too early, matter would have spread too thin for galaxies to form. The universe exists as it does because of a delicate balance, a cosmic dance between attraction and release, density and distance, pull and flow. It's a quiet reminder that even on the larger scales, equilibrium gives rise to beauty. Fact 55. What happens when gravity slows expansion locally? While the universe as a whole is expanding, not every region follows that rule perfectly. In some places, gravity becomes strong enough to resist the outward stretch of space. Take galaxies, for example. Within them, gravity binds stars together so tightly that expansion can't pull them apart. The same is true for galaxy clusters, vast families of galaxies held in one enormous gravitational hug. These are pockets where expansion pauses. Space between the clusters still grows, but inside them, gravity wins the local battle. Over time, this creates a cosmic pattern, a web of connected regions and empty voids, shaped by where expansion slows and matter gathers. It's a quiet interplay between two cosmic forces, the stretching of space and the strength that holds it together. Fact 56. How stars and galaxies resist the pull of the cosmic tide. Even though the universe keeps expanding, the stars above us don't drift away from each other. Galaxies don't rip apart and planets stay safely in orbit. Why? Because gravity, that invisible bond, holds them close. Inside each galaxy, the pull of gravity between billions of stars is strong enough to resist the gentle stretch of the universe. Think of it like a tide that's too faint to move a pebble near your feet. Space may be growing on the grander scales, but locally, gravity glues matter together. From the spiraling arms of galaxies to the steady orbits of stars around their centers. So even as the cosmic tide pulls the universe outward, stars and galaxies cling tightly, keeping their luminous shapes alive against the slow swell of eternity. Fact 57. The delicate balance that allows structure to form. The universe is a story of balance, not perfect stillness, but harmony between forces. Too much expansion too soon, and matter would have thinned into nothingness. Too much gravity too early, and everything would have collapsed before stars ever formed. Somewhere between those extremes, balance emerged. Tiny ripples in the young universe, barely measurable differences in density, allowed matter to gather slowly, forming stars, galaxies, and clusters. Expansion kept things from clumping too tightly, while gravity shaped them into patterns of beauty. Every galaxy, every star, and every atom of dust exists because of this cosmic equilibrium, a fragile yet lasting balance that gave rise to everything we see. Fact 58. Why expansion doesn't tear apart atoms or solar systems. People often imagine the universe stretching like a rubber band, pulling everything wider, even the spaces between atoms. But that's not how it works. Expansion happens between galaxies, across unimaginable distances. On smaller scales, like inside atoms, planets, or solar systems, the forces that bind matter together are far stronger than the pull of expansion. Atoms cling together through electromagnetic force. Planets orbit their stars because gravity dominates in their local region. The stretch of space is real, but it's faint. So faint that it only matters across the vast emptiness between galaxies. In the spaces where matter gathers, expansion pauses. The bonds of nature simply outmuscle the quiet pull of the cosmos. Fact 59. How galaxies remain bound. While space expands, imagine 2 points painted on a balloon. As the balloon inflates, the points move apart. That's what galaxies do on the grand scale, yet each galaxy itself stays the same size. Why? Because the stars inside are held together by gravity so tightly that the balloon stretching doesn't affect them. Galaxies exist like little islands of order in a growing sea. The ocean of space expands around them, but their own gravity keeps everything intact. Stars circling, gas clouds forming, light continuing to shine. Even as the distances between galaxies grow over billions of years, each one holds together a pocket of resistance within the flowing fabric of space. Fact 60. The quiet dance of local versus cosmic motion. The universe moves in two rhythms: the grand expansion of space itself and the smaller local motions of stars, galaxies, and clusters. While cosmic expansion pushes everything outward, local gravity makes galaxies spin, orbit, and sometimes collide. It's a bit like watching leaves float on a river. The river flows in one direction, but each leaf moves in its own small, swirling path. This quiet dance defines the universe we see. Galaxies drift apart over billions of years, yet within them, stars keep circling in calm defiance of the wider tide. It's a cosmic reminder that even in a universe always stretching, there are places where motion settles into balance, where stillness and movement coexist beautifully. Fact 61. The measurement units of the cosmos, megaparsecs and light years. In our everyday world, we talk about meters, kilometers, or maybe miles, but those units are far too small for the vastness of the universe. Astronomers need something much bigger. Light years and megaparsecs. A light year is the distance light travels in 1 year, about 10 trillion kilometers. It sounds enormous, but even that can feel small when talking about galaxies. So scientists often use megaparsecs. 1 megaparsec equals about 3.2 million light years. These measurements help astronomers map the structure of the universe, the spacing of galaxies, the expansion of space, and the distances to the farthest light ever seen. It's a reminder that the scale of the cosmos is beyond our daily sense of size. Even numbers lose their meaning out there, replaced by light, time, and wonder. Fact 62. Why expansion cannot be measured in everyday distances. When we say the universe is expanding, it's easy to imagine galaxies flying through space like cars on a highway, but that image doesn't quite fit. Expansion isn't about movement through space, it's about space itself stretching. That's why we can't measure it using normal distances or speeds. On cosmic scales, the rules change. The farther apart two galaxies are, the faster they seem to move away from each other, not because they're travelling, but because the space between them is growing. Everyday units like kilometers per hour simply can't capture something that happens to the fabric of reality itself. Instead, astronomers describe expansion using terms like kilometers per second per megaparsec. It sounds complicated, but it's just the universe reminding us. Its language isn't built for human scales. Fact 63. The use of standard candles like type Eos supernovae. Imagine trying to measure the distance to a lighthouse across a dark ocean. If you know how bright the light really is, you can tell how far away it must be by how dim it looks. Astronomers use the same idea with certain exploding stars called type Ia supernovae. These stellar explosions always reach nearly the same peak brightness, making them standard candles of the universe. By comparing how bright they appear from Earth, scientists can calculate how far away they are, and in turn, measure how the universe expands over time. Each flash of light from a distant supernova becomes a marker across billions of years, helping map the growth of the cosmos itself. Fact 64. How these cosmic mile markers. Revealed acceleration. In the late 1990s, astronomers studying Type Ia supernovae expected to find that the universe's expansion was slowing down, as gravity pulled everything inward. But when they compared supernova distances with redshift, a measure of how stretched their light was, they found something astonishing. The expansion wasn't slowing, it was speeding up. Those faint flashes of dying stars became cosmic mile markers revealing a hidden truth. Some mysterious force was pushing space apart faster and faster. This discovery changed cosmology forever and opened one of the deepest questions in science. What is driving that acceleration? Sometimes the universe speaks softly, through distant light that took billions of years to arrive, yet its message reshapes everything we thought we knew. Fact 65. The scientists behind the discovery of dark energy. Two research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, worked independently in the 1990s, both measuring distant Type Ia supernovae to map cosmic expansion. When they compared results, the conclusion was the same. The universe's growth was accelerating. It was a moment of shock and disbelief. Saul Perlmutter, Brian Schmidt, and Adam Rees led the efforts that confirmed it, earning the Nobel Prize in Physics years later. Their work revealed what we now call dark energy, a force that makes up most of the cosmos yet remains invisible and unexplained. Through careful observation and relentless curiosity, these scientists transformed tiny points of fading starlight into a discovery that changed humanity's understanding of everything, the unseen energy shaping the future of the universe. Fact 66. How the Nobel Prize honoured that revelation. In the year 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees, three scientists whose teams uncovered one of the most astonishing truths in cosmology: the accelerating expansion of the universe. Their discovery began with faint, distant points of light, Type Ia supernovae, scattered across the deep sky. These were ancient explosions so far away that their glow had travelled billions of years to reach Earth. By comparing how bright those supernovae appeared to how much their light had stretched, the scientists realized something unexpected. The universe's expansion was not slowing, as gravity would suggest, but speeding up. This quiet revelation transformed our view of the cosmos. It hinted at the existence of a mysterious unseen force, now called dark energy, filling space and driving everything apart faster and faster. When the Nobel Committee recognized their achievement, it wasn't just for a clever measurement or a new theory. It was for revealing a hidden truth woven into the fabric of reality, a truth that continues to challenge every physicist today. The award honored not only three brilliant scientists, but also the power of curiosity itself, the willingness to look at faint, flickering stars and ask what story their light might be trying to tell. Fact 67. The strange idea that the universe has no center. If the universe is expanding, you might imagine there's a center, a single point everything is rushing away from. But here's the strange truth. There isn't one. The expansion of the universe doesn't happen from a place. It happens everywhere at once. Every galaxy sees all the others moving away no matter where it is. There's no special point of origin, no cosmic center where it all began. A helpful way to picture it is to think of a rising loaf of bread. As it expands, the raisins inside all move apart, but no raisin is the center. The dough itself, space, is stretching. The Big Bang didn't happen in one location inside the universe, it happened to the universe. Space itself began expanding, and it still is. It's a concept that bends the mind. The universe has no edge, no middle, and yet everything in it keeps drifting apart. Evenly, endlessly, and everywhere. Fact 68. Why expansion looks the same from every point in space stand anywhere in the universe, on Earth, in another galaxy, or on a distant planet circling an alien sun, and you'd see nearly the same sight, galaxies moving away, their light stretched toward red. This isn't a trick of perspective, it's the nature of expansion itself. Because space is stretching evenly in every direction, every observer, no matter where they are, sees the same pattern. There's no front or back, no place where the expansion started or where it's heading. It's like dots drawn on the surface of an inflating balloon. From the point of view of any dot, the others all seem to move away equally. The balloon doesn't expand from one spot, It grows as a whole. That uniform motion is one of the key clues that our universe follows the same rules everywhere. It shows that space isn't just growing, it's doing so with remarkable consistency, a quiet rhythm playing across all of cosmic history. Fact 69. The concept of cosmic isotropy and homogeneity. Astronomers use two words to describe the large-scale nature of the universe: isotropy and homogeneity. Together they form one of the simplest yet most profound ideas in cosmology. Isotropy means that the universe looks the same in every direction, no matter where you look, north, south, or anywhere in between. The distribution of galaxies and cosmic radiation is remarkably even. Homogeneity means that, on average, the universe is the same everywhere. If you could zoom out far enough, past individual galaxies and clusters, you'd find that matter spreads out uniformly, like fine mist filling all of space. This idea doesn't deny the existence of stars, planets, or the grand filaments of galaxies. It just says that when viewed from a great enough distance, no region of the universe is special. The cosmos has no preferred direction, no chosen place. It's an elegant thought. Amid endless complexity, the universe remains beautifully consistent. Fact 70. The evidence that the universe is uniform on large scales. The idea that the universe is smooth and even might sound like an assumption, but it's one backed by powerful evidence. The first and clearest clue comes from the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light fills all of space and looks almost identical in every direction, with only the tiniest variations in temperature. Those small ripples eventually grew into galaxies and clusters, but the overall uniformity tells us that the young universe was astonishingly balanced. Another piece of evidence comes from large-scale galaxy surveys. When astronomers map millions of galaxies across billions of light-years, they see no pattern that suggests a center or an edge. The structure of the universe, the web of matter and voids, repeats statistically everywhere. So despite all its vastness and motion, the cosmos behaves like a single, well-mixed whole. It's as if the universe, in its earliest moments, set out to be fair, to spread its contents evenly, allowing no corner of space to feel more important than another. Fact 71. The possible shapes of the universe: flat, open, or closed. When scientists talk about the shape of the universe, they don't mean its outline like a ball or cube. They're talking about the geometry of space itself, the way light travels, the way distances curve, and how expansion behaves across unimaginable scales. There are three main possibilities. A flat universe means space follows ordinary geometry. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. An open universe has a saddle-like curve, stretching outward forever, where parallel lines slowly drift apart. And a closed universe curves back on itself, like the surface of a sphere, where travelling in one direction long enough could, in theory, bring you back to your starting point. Each shape tells a different story about the cosmos's destiny, whether it expands forever, slows down, or someday reverses. For decades, astronomers have searched for clues in light, gravity, and the cosmic background radiation, all to answer one quiet question: what kind of universe do we really live in? Fact 72. What flat really means in cosmic geometry. When scientists say the universe is flat, it doesn't mean two-dimensional. It means the geometry of space follows the same rules we learned in school, where straight lines stay straight and large-scale distances behave as expected. But this flatness exists on a cosmic scale, across billions of light-years. Space can curve around massive objects like stars or black holes, but when viewed across the entire universe, those tiny warps average out. A flat universe means there's just enough energy and matter to balance expansion and gravity perfectly. Not too much to make space curve inward, and not too little to make it curve outward. This delicate balance fascinates cosmologists. It suggests that the universe began with conditions so finely tuned that even the smallest difference could have changed its fate entirely. The word flat may sound simple, but behind it lies one of the most extraordinary balancing acts in nature. Fact 73. How expansion helps determine the universe's shape. Expansion is more than just a feature of the universe. It's a tool that helps reveal its geometry. By measuring how galaxies move apart, scientists can trace the influence of gravity, matter, and energy over billions of years. If the universe were closed, gravity's pull would eventually slow expansion, causing galaxies to drift closer again. If it were open, expansion would continue forever, growing faster and faster as space stretches endlessly. A flat universe sits in between, expanding forever, but always slowing slightly, balanced between infinite and finite. Astronomers compare observations of the cosmic microwave background, galaxy clusters, and distant supernovae to test these models. Every ripple of ancient light, every flicker of distant motion, becomes part of a grand geometric puzzle, one that tells us not just how fast the universe grows, but what shape its very fabric takes. Fact year 74. The infinite versus finite universe. Debate: is the universe endless, or does it curve back on itself like a vast cosmic loop? This question has challenged scientists and philosophers for centuries. If space is infinite, it stretches forever, with no edge, no boundary, and no repeating pattern. But if it's finite and curved, you could, in theory, travel in one direction long enough and eventually return to where you started, much like walking around the surface of the Earth. The challenge is that, no matter how powerful our telescopes, we can only observe so far, limited by the speed of light and the age of the universe itself. The rest lies beyond our cosmic horizon, hidden from view. So far, the evidence suggests that the universe may be extremely close to flat, so close that, if it is curved, the curve is too vast for us to detect. Whether that means infinite or just unimaginably large remains one of the greatest open questions in all of science. Fact 75. What cosmic background data suggests about infinity. The cosmic microwave background, the faint afterglow of the Big Bang, carries within it the fingerprints of the universe's shape. Tiny variations in its temperature and pattern reveal how space bends, curves, or stretches across the largest distances imaginable. When astronomers studied this ancient light, especially through satellites like WMAP and Planck, they found something astonishing. The data points to a universe that is incredibly flat. If the cosmos does curve, that curvature is so slight it must extend far beyond what we can ever observe, perhaps hinting at an infinite universe. It's a humbling thought. The light we see today began its journey nearly 14 billion years ago, yet it only touches a small part of something far greater. The evidence doesn't prove infinity, but it suggests that the cosmos might have no edge, only endless space, quietly expanding beyond every horizon we can ever reach. Fact 76. The idea of a multiverse born from eternal inflation. In the earliest fraction of a second after the Big Bang, the universe is thought to have expanded faster than light in a process called inflation. This wasn't just ordinary expansion, it was a sudden, explosive stretching of space itself. Some theories suggest this inflation never truly ended. Instead, while our part of space slowed down and cooled, forming stars, galaxies, and everything we know, other regions kept expanding. Each pocket that stopped could have become its own separate universe, with different physical laws or constants. This idea is called eternal inflation, and it leads to a breathtaking possibility that our universe may be only one bubble in an endless cosmic sea, a multiverse. We may never see these other universes separated forever by inflating space, but the concept changes how we think about existence. It reminds us that what we call the universe might not be everything, just one small island in an infinite cosmic ocean. Fact 77. Why cosmic expansion might never end. Astronomers once thought gravity would eventually slow the universe's growth, perhaps even reversing it. But the discovery of dark energy changed that view entirely. This mysterious force filling space itself pushes galaxies apart, and its strength doesn't weaken over time. As space grows, more of it appears, and with it, more dark energy. That means expansion doesn't fade, it accelerates. If this continues indefinitely, the universe will never stop expanding. Galaxies will drift farther and farther apart until, Eventually, only the nearest stars remain visible. The night sky will grow darker, and distant light will fade beyond perception. It's a quiet, almost poetic fate, not an ending marked by fire or collapse, but by the steady stretching of space into stillness. Fact 78. The scenario of the Big Freeze. Among all the possible cosmic endings, the Big Freeze is one of the most widely accepted. It's not dramatic. There's no explosion, no sudden collapse. Instead, it's a slow, inevitable fading. As the universe expands, galaxies drift so far apart that their light can no longer reach each other. Stars burn through their fuel and die, leaving behind cold remnants, white dwarfs, neutron stars, and black holes. Over unimaginable spans of time, even black holes may evaporate, releasing their last whispers of energy into an ever-cooling void. The universe continues to expand, but its contents grow dimmer, slower, colder. Eventually, the cosmos becomes a quiet sea of thin radiation and darkness, a place where time still passes, but nothing changes anymore. It's the ultimate stillness, a frozen eternity. Fact 79. How stars will fade in a far-expanding future. Right now, the universe is filled with light, from blazing suns, glowing nebulae, and galaxies scattered across billions of light-years. But this brilliance won't last forever. Stars are engines of fusion, and even the longest living ones eventually run out of fuel. Billions of years from now, new stars will form less often as galaxies lose their gas. The big bright ones will vanish first, leaving smaller, cooler stars, faint red dwarfs, that burn for trillions of years before fading into black embers. Over countless ages, the universe's glow will dim to nothing. Only cold remnants will remain, drifting through expanding space. The last light to shine might come from the slow evaporation of black holes, brief sparks in a darkening cosmos. After that, silence. The stars will have said their final goodbye. Fact 80. What a dark, cold universe might be like. Imagine a time so distant that galaxies have faded, stars have died, and even black holes have dissolved into faint radiation. That's the far, far future, a universe cold and nearly empty, where expansion has stretched space beyond recognition. In that era, there will be no starlight, no warmth, only the faint hiss of leftover energy spread across endless distances. Time will continue, but with nothing left to measure its passage. Matter itself may decay, leaving behind only stray particles drifting through the quiet dark. It's hard to picture such stillness, a cosmos once full of brilliance and motion now resting in absolute calm. Yet even that cold emptiness tells a story. Everything that was once born from the Big Bang will have completed its journey, returning to silence. The universe's final act may not be destruction, but peace. Fact 81. Alternative endings, the Big Crunch and Big Rip. The future of the universe isn't written in stone. While the Big Freeze remains the leading theory, two other dramatic endings have long been debated, the Big Crunch and the Big Rip. The Big Crunch imagines a universe where gravity eventually overcomes expansion. Galaxies would stop drifting apart and start moving closer, collapsing everything back into a dense hot point, perhaps leading to another Big Bang. It's a cosmic rebirth scenario, where the end might spark a new beginning. The Big Rip, on the other hand, is far more violent. If dark energy grows stronger over time, it could accelerate expansion so much that galaxies, stars, planets, and even atoms are torn apart. Space itself would stretch faster than any force can hold together, a universe literally ripped from within. Both scenarios show how delicate the cosmic balance is. A small change in the strength of expansion or gravity could completely rewrite our universe's fate. Fact 82. How expansion determines the universe's destiny. To understand how the universe will end, scientists first study how fast it's growing. Expansion isn't just a moment in time, it's the key to everything that follows. If expansion is slowing down, gravity might one day pull everything back together, ending in a collapse, the Big Crunch. If expansion continues at a steady pace, the universe will drift toward the Big Freeze. And if it accelerates forever, it could lead to the Big Rip. every galaxy's motion, every shift in the light that reaches us, helps trace this cosmic story. It's as if the universe is writing its own future across the night sky, one wavelength at a time. The expansion rate doesn't just measure how big the universe is, it decides whether the cosmos ends in fire, ice, or a tearing storm of space itself. Fact 83. The role of dark energy in that fate. Dark energy, the invisible force driving cosmic acceleration, is the deciding factor in the universe's destiny. Though it makes up about 70% of the cosmos, its nature remains one of physics' greatest mysteries. If dark energy remains constant, expansion will continue forever, leading to a slow fade into darkness, the big freeze. If it weakens over time, gravity might eventually win, bringing about a big crunch. But if it grows stronger, expansion could speed up without limit, tearing the universe apart in a catastrophic big rip. Scientists measure the equation of state of dark energy, how its pressure compares to its density, to test these outcomes. Every new observation, from distant supernovae to background radiation, helps narrow down which cosmic ending awaits. For now, evidence suggests dark energy remains steady, guiding the universe toward a quiet, endless expansion. Fact 84. How scientists test cosmic theories using simulations. The universe is far too large and slow-changing for us to watch its evolution directly. Instead, scientists use powerful computer simulations to compress billions of years into digital form. These simulations start with known physics, gravity, dark matter, radiation, and expansion, and then evolve the universe step by step. By adjusting conditions like dark energy's strength or the density of matter, researchers can watch how galaxies form, merge, or fade over time. The results are then compared to what we actually see in telescopes. If a simulation matches reality, the clustering of galaxies, the shapes of cosmic filaments, the expansion rate, it strengthens that theory. It's like running the universe on fast-forward again and again until we find the version that looks most like home. Fact 85. The expansion data collected by the James Webb Telescope. The James Webb Space Telescope, JWST, has given scientists a new window into the early universe, and with it, new clues about expansion. By capturing light from the first galaxies formed just a few 100 million years after the Big Bang, JWST lets astronomers measure how quickly the universe was expanding at different points in its history. These observations test the Hubble constant, the rate of expansion, and help resolve long-standing tensions between past measurements. Webb's infrared vision sees farther and older than any telescope before it, revealing galaxies so distant that their light has been stretched, or redshifted, across billions of years of expansion. Each observation adds another data point to the cosmic timeline, bringing us closer to understanding not just how fast the universe grows, but where that growth might lead. In the end, the James Webb Telescope isn't just looking backward in time, it's helping us glimpse the future of everything. Fact 86. How deep-field images reveal billions of galaxies. When astronomers first pointed the Hubble Space Telescope toward what seemed like an empty patch of sky, no one expected much. That small, dark window, barely the size of a grain of sand held at arm's length, revealed something breathtaking: thousands of galaxies. This image, known as the Hubble Deep Field, changed how we see the universe. Each faint speck of light wasn't a star, but an entire galaxy, each holding billions of stars, planets, and perhaps other worlds like ours. Later, the ultra-deep field and now the James Webb Deep Field pushed that vision even farther, showing galaxies so distant that their light began travelling toward us billions of years ago, when the cosmos was still young. These images remind us that what we see above isn't empty at all. It's overflowing with creation, spread across unimaginable distances. Even the smallest corner of the sky contains more galaxies than we could ever count, a reminder that our universe is far more vast and alive than the eye can see. Fact 87. The sense of scale. When viewing the early cosmos, trying to grasp the scale of the universe can feel impossible. The galaxies seen in deep-field images appear tiny and distant, yet each one could span hundreds of thousands of light-years. Their light took billions of years to reach us, meaning we see them not as they are now, but as they once were. Imagine holding a photograph of someone taken when they were a child. Now imagine that photo is made of light that has been travelling for over 10 billion years. That's what we see in these cosmic portraits. Every deep field image is like a time window, capturing an era when galaxies were still forming. The farther we look, the younger the universe becomes. What began as a glowing sea of energy slowly cooled, separated and formed stars. The first building blocks of everything to come. Each image brings both wonder and humility, a feeling that we are part of something endlessly larger, still unfolding across time. Fact 88. The faint light from galaxies formed billions of years ago. The light that reaches us from the earliest galaxies is unimaginably faint, stretched thin by the expanding universe, dimmed by distance, and redshifted beyond human sight. To capture it, telescopes must stare at one patch of sky for days or even weeks, collecting each photon, the smallest unit of light, like a treasure. What emerges from that long watch are ghostly smudges of red and gold, evidence of galaxies born just a few 100 million years after the universe began. Those ancient lights tell a story written in colour and distance. The faintest ones show the universe's youth, when stars first began burning hydrogen, when dust and gas swirled into early clusters, and when gravity started shaping the cosmic web we know today. Every faint glimmer we detect is a message from the beginning, a soft echo from a time before Earth existed. Fact 89. How expansion makes those galaxies appear redder. As the universe expands, it stretches the very light travelling through it. This stretching increases the wavelength, shifting the light toward the red end of the spectrum, a phenomenon known as redshift. For distant galaxies, this effect is enormous. What began as bright blue light from young stars now reaches us as deep infrared, invisible to human eyes but captured by telescopes like James Webb. Redshift is more than just a change of colour. It's a measure of time and distance. The higher the redshift, the farther the light has travelled, and the older the universe was when it left its source. In a way, cosmic expansion has painted the universe in softer tones, turning the fierce brilliance of its youth into the calm, reddish glow we see today. Fact 90. The poetic beauty of seeing the universe's past in its light. When we gaze at the stars, we aren't seeing the present, we're seeing the past. Every glimmer of a light is a story that began long ago. A nearby star's light might be a few years old, the light from our galaxy's centre thousands of years old, and the light from distant galaxies billions of years old. Through telescopes, we witness time itself, stacked layer upon layer, like pages in an endless cosmic book. The beauty of this isn't just scientific, it's deeply poetic. To look into the universe is to look into memory, into the first sparks of existence, still crossing the darkness to reach us. Each photon that touches our eyes tonight has travelled across expanding space since before our world formed, and somehow, across all that time and distance, it still carries the gentle warmth of creation's beginning. Fact 91. How cosmic time flows. Differently. Across the universe, time, as we know it, isn't as steady as the ticking of a clock. In the universe, time itself bends and stretches depending on where you are and how fast you're moving. In places with stronger gravity, near stars, black holes, or dense clusters of matter, time slows down compared to regions with weaker gravity. This isn't imagination. It's a proven effect of Einstein's theory of relativity. A clock near a massive object literally ticks more slowly than one floating in empty space. Across billions of light years, the universe's expansion adds another layer. As space stretches, it also stretches how we experience time. Light travelling to us from distant galaxies has been moving through a changing universe, where time itself expands along the way. So when astronomers look across space, they aren't just seeing distance, they're peering through layers of time flowing at different rates. The cosmos is like a vast river, with currents that twist, slow and surge in ways we can only begin to understand. Fact 92. Why looking far means looking back in time. When you look at the moon, you're seeing it as it was about 1 second ago. The sun, 8 minutes ago, The light from the nearest star left more than 4 years ago. That's because light, even though it's the fastest thing in existence, takes time to travel. So when astronomers observe galaxies billions of light years away, they're seeing them as they were billions of years in the past. In a sense, telescopes are time machines. Each deeper observation reveals an earlier chapter of cosmic history. The young stars, the forming galaxies, the first atoms glowing in a newborn universe. This idea changes how we see everything above us. The farther we look, the further back we go, tracing our way through time itself toward the beginning of space and all creation. Fact 93. The idea that the night sky is a window to history. Every night, when you step outside and gaze upward, you're not just looking at stars, you're looking into the past. The sky's a living record of the universe's story written in light. Each twinkle comes from a different time, some from a few years ago, others from thousands or millions of years ago. Even the faintest glow that reaches our eyes tonight began its journey before humans existed. That's what makes the night sky so extraordinary. It's both present and ancient at once. The light that fills it has crossed expanding space, dodging dust clouds and galaxies, surviving for eons to meet your eyes at this exact moment. So the next time you look up, think of it as opening a cosmic diary, one written in starlight, each page a memory of how the universe once was. Fact 94. How every star carries a story from the expanding past. Each star you see tonight was born from the remnants of earlier stars, generations of creation and destruction that stretch back billions of years. Their light carries not just beauty, but history. Some of those stars are racing away from us as space expands, their light stretched into longer wavelengths, a redshift that records the universe's continuous growth. Others are younger, formed in newly spun galaxies, lighting up fresh chapters in the cosmic story. When we study their colour, brightness, and composition, we decode time itself, finding traces of hydrogen from the Big Bang, heavier elements from supernovae, and clues about how expansion shaped everything we know. Every star is like a storyteller, whispering across the cosmos about where it came from and where it's going. A reminder that even the smallest shimmer in the sky connects us to the deep rhythm of the expanding universe. Fact 95. The soothing rhythm of cosmic expansion. Through eons, over billions of years, the universe has expanded with a quiet, steady rhythm. Not a sudden rush, but a long, graceful unfolding. Galaxies drift apart like dancers slowly moving across an endless stage, their motion silent but full of meaning. Even as stars are born and die, as light travels across immeasurable distances, the overall pace remains calm, a cosmic heartbeat that never stops. The same process that began in the first moments of creation continues today, stretching space and carrying galaxies ever farther from one another. There's something deeply peaceful in that. The expansion of the universe isn't chaotic, it's patient, unhurried, and vast. To think that everything, stars, planets, and even us, drifts gently with that rhythm is almost comforting. It's a reminder that we're part of something timeless, something still unfolding with quiet grace through endless eons of cosmic time. Fact 96. The humbling idea that we live in one brief cosmic moment. When we think about time, we often imagine decades, centuries, or maybe the span of human history. But in the age of the universe, more than 13 billion years, even all of human civilization is just a heartbeat. Our entire story, from the first sparks of fire to exploring space, has unfolded in a blink of cosmic time. Stars live for billions of years, galaxies drift for even longer, and here we are, existing in one fleeting instant, able to look up and wonder how it all began. It's humbling and beautiful to realize that we are part of something so much greater, something that existed long before us and will continue long after. Yet in this small moment, we are the universe becoming aware of itself. That's not small at all. That's everything. Fact 97. The fact that everything, stars, planets, people, arose from expansion. When the universe began expanding, it didn't just stretch. It created the conditions for everything that would ever exist. Out of that early burst came particles, then atoms, then stars that fused those atoms into heavier elements. Over billions of years, those elements formed planets, oceans, and eventually, life. Every atom in your body was once part of a star, born in the furnace of cosmic expansion. The calcium in your bones, the iron in your blood, the oxygen you breathe, all forged in stars that lived and died long before Earth was formed. Expansion wasn't just a movement, it was creation in motion. Every sunrise, every mountain, every breath we take traces back to that first moment when space itself began to grow. We are, quite literally, made from the fabric of the expanding universe. Fact 98. How cosmic motion continues silently all around us. Right now, as you read this, galaxies are gliding farther apart. The Milky Way spins through space, stars orbit its centre, and even the atoms in your body drift along with the cosmic flow. And yet, we feel none of it. The motion of the universe is vast, silent, and gentle. It doesn't roar or shake, it simply is. Space expands quietly, everywhere at once, carrying everything along. There's something soothing in that. The thought that all of existence moves together, gracefully and endlessly. Even when we feel still, we are part of a silent, universal dance that has been going on since the dawn of time. Fact 99. The thought that expansion means creation is ongoing. Many people think creation was a single event long ago, a flash, then calm. But the truth is, it never stopped. The universe is still expanding, still forming stars, still shaping galaxies. Every new cloud of gas that collapses into a star, every planet that forms from dust, every light that flickers into being, it's all part of that same ongoing story. Expansion didn't just make the universe, it keeps making it. In a way, creation is always happening around us. Each new sunrise, each starlit night, each spark of curiosity, all reminders that the universe continues to build, grow, and unfold, one moment at a time. Fact 100. The gentle reminder, as the universe expands, so does our sense of wonder. The more we learn about the universe, the more mysterious it becomes. Every discovery, from distant galaxies to invisible energy, reminds us that our curiosity can expand just as endlessly as space itself. There's peace in knowing that we don't have to understand everything. We can simply marvel at the stars that have burned for eons, the galaxies drifting in silence, and the fact that we are here to witness it at all. As the universe stretches outward, so does our wonder. It reaches across time and imagination, reminding us that curiosity is part of what makes us human, and part of what makes the cosmos so endlessly beautiful.